You should have it looking like this. Okay, this is like Survivor class. We're down to the last few people. Okay, so yes. Go ahead, answer, Lauren.
Like answer it?
Yeah, speed and velocity.
Speed is how fast the thing is moving, and then velocity is how fast the thing is moving at like a specific rate.
All right. So speed. And then velocity is speed with a direction. Okay. So if you say you're going 60 miles an hour, you're telling me your speed. If you say you're going 60 miles an hour traveling north, you're giving me velocity. That's the only difference. You're just telling a basic idea of which way the object is going. Okay, so let's take a look at these problems down here. It says, how far can a person run in 15 minutes? Okay, it says how far, and we know that our speed formula is distance divided by time. So if the question is how far, what are we going to be solving for? Yes, distance. All right. And that might seem silly for some of you to think about, but there's a lot of times where I'll give quizzes and tests and people say, I don't even know where to start. I don't even know what we're trying to find. It's a good thing if you don't know what you're trying to find, you're probably not going to find it, right? So make sure that you are able to define the variables and you know what the problem's asking for. All right. So since that is the case, if we multiply both sides by time, time cancels on the right side, and therefore, boom, boom, boom. Sorry, I don't know what that is, but we will ignore. And time multiplied by speed will be our distance. So now, the only thing, yes, the only thing to pay attention to that could trip you up is you see minutes and kilometers per hour. So you're going to have to pick one of those. You have to pick whether you want to do it in minutes or hours. It really doesn't matter which one you do. But it's a lot easier, I would think, just to make minutes into hours. But so 15 minutes is 0.25 hours. So speed times time, you have 16 kilometers per hour. Dang it. Times the time, which is 0.25 hours. So then, Daniel, how much is that?
4 kilometers.
About 4 kilometers. All right. Okay, number 7. Okay, snail can move approximately 30 or 0.3 meters per minute. Little snail. Not very fast, that's all right. How many meters? Okay, so how many meters, that tells us what are we trying to find? Distance, right? Okay. Can the snail travel in 15 minutes? So we're going to use the same setup as we did here. Right here. Okay. Divided by speed equals distance. So Therefore, 15 minutes, and this one you don't even have to change, which is nice. Okay, so then that will equal what? How many meters? 4.5 meters. Okay, any questions on that? All right, let's go ahead and take one quick look at our homework and make sure we're all happy on those problems. You can ask whatever you want on this, but the one I did want to make sure that everybody sees is this one right here.
What is that word?
What is the definition of the word per? What does per mean? Yeah,
Is this per sort of like miles per hour?
right. And we say that all the time, right? But what does it mean? What do we mean when we say per? Yeah.
Miles every hour.
Miles every hour.
It's also like you almost say it's like a green sign.
Yes. Yeah, you can almost, not just almost, but you can say it's division. Every time you hear the word per, think division. Per, divide. Put those two together in your brain. Every time you hear per, divide. Right? So, if it's per, either you're going to have to do the, mathematically you're going to have to divide, or the units are going to be one over the other. All right? So, we'll just write division in here. All right? So, other than that, how did you all do on the rest of these? Any questions on those? Any ones that you couldn't do, Daniel?
You do number 7, please.
Number 7? Okay. It says, how much time would it take the sound of thunder to travel 2,000 meters if, and we had the speed before, right? If sound travels at a speed of 330 meters per second. So, if we have our formula is distance divided by time, what are we solving for? Which value of that are we solving for? How much time, right? That tells you it right there. So we're going to solve for t. So it's a little bit harder. I like to do it this way. There's other ways to do it, but so then t multiplied by v will equal d. And if we're going to solve for t, then we can just divide both sides by v, or speed. V and s interchangeable. Therefore, time is distance divided by velocity. Okay, or divided by speed. So, we're going to use that formula right here in our problem, where we have 2,000 meters in that. Make sure on that. Time is 2,000 meters over. I really need to replace the cap on this pen. Divided by 330 meters per second. Those meters will cancel, and seconds is in the denominator, so it's going to go to the numerator. And 2,000 divided by 330 is what? 6.1 seconds. All right. Got it? All right, so everybody good on those? Given an opportunity next Thursday and a couple problems just like these, you'll do perfectly well 100% on them, right? No problems. No problems at all with the problems. All right? Okay, good. I look forward to it. Okay. Now, if you would, I gave you more gifts. In the class notes, you have something called speed graphs. Let's go to that. Okay? Yes?
I have one question about this thing. So like, are we gonna have to know like the definitions of like speed and velocity and like all the other stuff, or just like?
I very, very rarely, and if you heard on the video, question was whether or not you need to know definitions of these words. And I don't often ask like specific, what is the definition of blah, 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 blah. But in order to answer other questions, you're going to need to know what they mean. So you'll use the definitions to solve the problems. So I would know what they mean. But there's not a ton of words this time yet.
For the kids, is it gonna be like this stuff, or is it gonna be everything we've learned since the last?
When I put on portals, I put equilibrium, free body diagrams, speed problems, and then graphs, which is what we're doing today. So yeah, so pretty much everything that we've done since density will be on it. Okay. So, any other questions before we move forward? All right. Okay. So we're going to look at distance versus time graphs. The speed is the distance an object travels per unit of time, and this is graphically representing this speed. All right. So this is our person here, right? So we can say that this person is walking somewhere. I don't know. Let's say for whatever reason we decided we're going to send Savannah down to the office, and if we're going to keep track of her movement, we can like take pictures every, I don't know, man. According to this, it's every 50 seconds. Maybe we do less than that, maybe 10 seconds, whatever. We would see how far during each interval that Savannah would move. Okay? Now, in this case, right, you see in 50 seconds that this person moved. We'll make it Savannah, maybe give her longer hair. I don't know why her hair is red, but whatever. It's fine. Okay, so this is Savannah, and she's walking along, and every 50 seconds, then obviously she's traveling 50 meters. All right. We get smaller intervals in there. Either way, we're going to start to put those points onto the graph, and we're going to come up with lines, right? And when we do that, this is how we're going to set up our distance versus time graphs. Or, get out of there. Sorry. Now, you notice that the distance is on the y-axis and the time is on the x, always. Okay? So that means which of these two is the independent variable? Remember? I know it's been a while. Time, right? So the x-axis is always the independent variable. All right. Now, that means that that's the one that we pick and choose on, right? And that makes sense because if we're standing here and we're running our experiment and we're having Savannah walk, we can't control how fast Savannah walks, right? We can't make her walk faster, slower, whatever. That's not something that we do, right? We can't control how the distance that she travels, but we can control the time intervals that we pick to chart her path. And it's a lot easier to do that than to come up with some distance, right? And say, well, when you cover this distance, we'll do the time, right? It's a lot more difficult to do. So time is almost always the independent variable in these situations, right? So that therefore it goes on the x-axis, and on the y-axis is distance, all right? Now, one thing that I want to point out to you is this time 0. Okay? When we have time at 0, that just means that that's when we start keeping track of the time. It doesn't mean anything other than that, right? Obviously, it's not the beginning of time when we start our experiment. And it's not real time 0. It's whatever we as experimenters decide is the time to start it. Okay, it would be when she starts, right? And the distance is also subjective. It's something that we pick, right? So if we were seeing the distance from here to the office and how much time it takes you to do that, then our distance 0 would be right here. Because this is where she started, right? It can be something else if we wanted, but this makes the most sense usually. Because that's when the object starts with that we're measuring, but so we take the 0. Just recognize when we say 0, in most cases, especially distance and time, that it's relative and it's something that we choose rather than having any physical significance, right? So, because as we talked about last time, our point of view is crucial, right? And you'll see why that is in a minute. Okay? So, if we started to plot these distances, and what's happening to the distance in this graph? Yeah, Daniel?
It's staying the same.
It's not changing, right? Okay, so assuming this isn't 0 distance, this is what's happening in the graph right now, just right now, here, right? She's not moving. She's not going anywhere. So that's what that is. Right? And the distance, whatever the distance is, it's not changing. Right? So if this were her walking, this is like maybe she's walking along and she stops to get water. If she's getting water, time's passing, her distance still isn't going to change at that point. She's not moving forward. Right? Okay? So one of the things that you all are going to have to be able to do as we go along here, especially next Thursday, is looking at a distance versus time graph, and just based upon the line and the curve of the line, tell me what's happening. Is the person moving forward? Are they at rest? Whatnot. Right? So when you see this plateau on a distance versus time graph, that means the object is at rest. It's not moving. Okay? Now, moving forward. If Savannah, our object, is moving at a constant rate of speed, then the graph will look something like this. Because for every interval of time that we're measuring, she, roughly speaking, moves forward at the same distance. Right? That's what a constant speed is. If we're doing maybe every 5 seconds, she's going to move the same number of meters forward for every 5 seconds that we pick. If she maintains the same speed, therefore the line will look like this. Now, here is an important point. And let's look at this first. Yeah, and this describes just what I said. If the intervals are all the same, you're going to get a nice straight line, right? Now, we start to talk about a constant and positive slope. What is slope? Well, remember, slope equals y2 minus y1 divided by x2 minus x1. Whatever we pick on there, right? Whatever points that we pick on there. So, if we look back at this one and the other one, if we have y over x, we have distance over time. And if we're dividing distance by time, what do we get? Speed. Therefore, the slope of this line is speed. Whatever the slope of the line is at any point along the line, that is the speed of the object. All right? That's another thing to get in your head. You see distance versus time, you see a line, you say, okay, the slope of that line is speed. Every time. All right? That's the significance of it. So, if you have a constant slope, that means you have a constant speed. Now, that also means, going down here, let's say these are 2 different Savannah trials. What's the difference between A and B? What is she doing differently? Yes, Daniel?
She's going at a higher speed.
Right. She's walking faster, maybe jogging and be something. So as the slope gets bigger, the slope of speed, the slope increases, speed increases. All right. Again, that's looking at the graph and telling what's going on in the graph. Bigger slope, faster object. All right. And the opposite is true. All right. If we had a line that was here, all right, we'd say maybe she didn't really want to go to the office that much, so she's got to take her time, going as slow as she can to get there, right? As that line gets closer to that x-axis, it's a slower object. Okay? All right. Important point. Now, let's take a look at this down here. All right, and you look at this and you say, "Oh gosh, that just looks perfectly like a test or quiz question, doesn't it?" Give the graph and say, "Okay, tell me the slope of these points. And tell me how fast the object is moving at this point." Probably wouldn't even say slope, because I expect that you know when you see position versus time or distance versus time that slope means speed. So I just say the speed. What's the speed of the object between 2 and 4 seconds? And what's it doing? Well, firstly, what is it doing between 2 and 4 seconds? Daniel?
Increasing speed.
Careful. Is that a constant slope? Does the slope change between 2 and 4 seconds?
Yeah.
It does?
It's going.
Well, it goes up, but the slope itself doesn't change. The slope stays the same. But what is the object doing? If this were our Savannah circumstance, what would she be doing? Yeah? Going to the office. Moving forward. Right? Now, what's forward? Well, in this case, it would be from her seat to the office. That's forward, or the positive direction. So that's all I would write there. Is she's moving. Okay. I like to be super concise with my words sometimes, especially when I write them down. Moving. How do we know that she's moving? Because it's not flat, right? It's not a flat slope. So yeah, it's got to be moving. And we know it's moving forward because it's a positive slope. All right. So that's the answer to the first question. The second question we'll do out here. What's the velocity? Now, how can we find the velocity or the speed? Yes.
Distance divided by time.
Get the distance divided by time of the line of the. So we're doing the slope between 2 and 4 seconds. Okay. So the the y values, the y at 4 seconds is what? Yes.
Is it 54?
It is 54 meters. And how about the y at 2 seconds? Yeah.
18.
Good. 18 meters. So we have 54 minus 18. And the 54 meters was at 4 seconds. And the 18 was at 2 seconds. So we have 2 seconds on the bottom. And what's on top? 54 minus 18.
46. 36. Dang.
It's okay. Right? 36 meters divided by 2. So that will be 18 meters per second, and that will be a positive value. Now, the significance of the positive is that it's moving forward. Okay? Yes?
So if we get it, so if we don't put the positive and negative, do we get it wrong?
Well, the negative, yes, just by, the accepted way of doing things in your math classes is if you have a positive value, you don't typically put the positive on there. But if it's negative, you need to have it. That's why I put the positive in parentheses. Because you wouldn't necessarily always put positive. If you do, it's not wrong. But I just like to do it just to emphasize that that's important. Important to recognize that it's positive versus the negative. Because we're talking velocity now, we're given a direction. All right? Any questions on that? Now, also notice, by the way, before I move on to the next one, this doesn't say that she necessarily walked straight to the office, right? She does it in a consistent manner, but she could be talking to people along the way. Maybe she talks to people and then walks fast. Who knows? All right. But the point is, for that interval, that's how fast she's moving overall. All right. So, B, we got 6 to 7 seconds right here. What is she doing? Yeah. Stand still, right? Maybe this is where she gets to the office. She's waiting for whatever she's doing there. I don't know why she's at the office, but waiting for something. Okay? So, 6 to 7 seconds, we would say that she's at rest. That's the fancy physics way of saying it. The object is at rest. It's not moving. All right? Because you had that flat plateau graph. Now, we can probably guess without even calculating what the velocity will be, but we'll do it anyways. What's the velocity? 0 if it's at rest, right? But let's prove to ourselves that that's the case. So at y2, so that would be 7 seconds, it's going to be 72 meters. And at y1, it's also 72 meters. And this was 7 seconds, and this was 6 seconds. All right, so that means 0 over 1 second. Therefore, 0 meters per second. All right, that's why it's at rest, because that distance isn't changing, and it's distance divided by time. So the distance is not, the distance is not changing, so the speed has to be 0. Now, I guess it's conceivable somehow that the time would be 0, although that's unlikely. Should make the speed infinite, but anyways, more on that later. So finally, letter C. And the object doing between 8 and 10 seconds. Give her these little marks. We have 8. That's terrible. Is right here, and 10 is right here. So at 8 seconds, I'm sorry, but let's first say C, what is it doing? Eight to 10 seconds. So what's different about that? Don't forget the reality. What? Going back, right? So she went to the office, does what she is, and then she's coming back to this spot. That's why the slope is going down instead of going up. Okay? So we say moving backwards. Okay, so at 10 seconds, what's the position? Is it about 66 meters? And then at 8 seconds, what's the position? like 42-ish.
Oh, I think you flipped them.
Oh, yeah, I'm sorry. Too worried about this stupid stylus. A couple of days ago was making an important point in the class and it flew out of my hand. And then the tip of it broke, and now it's all wiggly on me. Okay, so we have 10 seconds minus 8 seconds. So that's going to give us negative what? Over 2. Huh? Okay, so then that'll be about negative 12. Okay, so now that just means the 12 meters per second means that's how fast she's moving, and the negative means that she's moving backwards. All right, she's moving forward faster to get to the office than coming back to class. Maybe she just didn't want to come back to class as much as, I don't know, but for whatever reason, that's the case. All right. So, any questions on that before we move forward? All right. Now, what I do quickly, and this is, we're just going to look at the first bit of this. You look at the acceleration notes that I passed out to you. This top part here, right? I would say, you should know those, okay? Because if you look at that, that's just what I was mentioning before, right? You have a constant speed, you have a constant slope. You have the speed changing, you're going to have the slope is changing, right? These are well, actually, let's go back to the other one. You look at here, look at these points right here. Right? See how you got those little curves there? You have a distance versus time. That means that's not a consistent slope, right? And this makes sense because, when somebody is going to stand up and start walking, they don't stand up and they're at top speed right away. They have to get up to speed, right? And then, before they stop, they're going to slow down. Yeah. So, and then we'll accelerate in the opposite direction for the third curve there. So those little curves tell you that you have a change in speed. Now, what's the term for a change in speed? Yes. Acceleration, right? And we'll replace that with velocity, but good enough. Is a change in velocity. Anytime velocity changes, speed changes, you have an acceleration. Now, in physics, whether it's speeding up or slowing down, we call them both acceleration. It's just a positive or a negative acceleration. That's all. We'll get more on that later, but just be aware of that terminology. All right. So, therefore, when you see, you should be able to see something like this and predict these different situations. Okay? Questions on that? Now, all right, so I guess that's the end of class. So everybody say goodbye to Maya and Ashley and Kale. Bye. See ya.